Hello students, in today's lesson, we are going to look at two more public key crypto systems. One is Elgamal cryptographic algorithm and the other is Knapsack cryptographic algorithm. Okay, so let's look at Elgamal encryption first. Okay, so Elgamal is a public key crypto system. It uses asymmetric key encryption for communication. So there is a public key and a private key. We know all that already, to communicate between two parties and to encrypt the message. The math used over here is discrete logarithms. Okay, the security itself is based on the difficulty of finding discrete logarithms in cyclic groups. So when Elgamal encryption is being done, we first select a group and we select a particular prime, and with that we do the rest of the calculations. Because it is difficult to find the G raised to G is group, okay? So G raised to A, if you do not remember discrete logarithm groups, please go back and revise it. Otherwise, you will not understand what I'm saying over here and how these calculations are being made. Okay, please go through the math and then come back. G raised to A of K is the actual key that is going to be used. And we send over the, internet, we send G raised to A and G raised to K. But just because we know G raised to A and we know G raised to K, it is not easy to compute G raised to AK, which is the actual key that is going to be used for encryption. And because that problem is a difficult problem or a hard problem, the encryption is secure. Okay, so we are going to look at what are the steps in encrypting in the Elgamal crypto systems. There are 3 steps basically. So supposing Alice wants to communicate with Bob. Okay, so Alice wants to send a message to Bob. So with PKC itself, we know that if A wants to send a message to B, A has to take B's public key and then do the rest of the encryption operation. Okay, so if Alice wants to communicate with Bob, Alice should know Bob's public key. Okay, so the first step is Bob generates his public and private keys. And the steps for generating the public and private keys are shown below. Okay, the first thing that Bob does is Bob chooses a very large number Q and a cyclic group F of Q. Okay, so he chooses a very large number Q and a cyclic group F of Q. From the cyclic group F of Q, he chooses one element called G. And this G, he chooses 2 elements. He chooses any element G, and with the details that they already have, an element A is chosen such that the GCD, okay, the relative GCD A comma Q is equal to 1. So this element A and this number Q, they should be relative primes. If GCD A comma Q is equal to 1, that means these 2 numbers A and Q are relative primes. Okay, so first Bob chooses a large number Q and the cyclic group F of Q. From the cyclic group F of Q, he chooses a random number G and another element A, but the element A has got the condition that A and Q must be relative primes. Okay, then what he does is simple. He simply calculates G raised to A, which is computed as H, and Bob publishes the cyclic group which he has used, the number Q which he has selected, and his public key, G raised to A. Okay, he doesn't send G and A separately. He sends the value H. Okay, so G raised to A is sent over the internet. So F, G, and Q are the F, H, and Q are sent over the internet. Okay, here G raised to A is actually his public key. Okay, so, G is his public key and A is his private key. So G is known publicly and A is kept private. Okay, so this is the first step. So if you want to communicate with Bob, the first thing that we need to know is his public key. That can be known only if he has published his public key. Okay, so these are the steps for any user, A or B or C, to generate his public and private keys. Okay, now once the public key has been, published, then the second step is Alice encrypts data using Bob's public key. So Alice selects an element K from the cyclic group F, which was sent by Bob, which is the information is there with Bob's public key, such that this number K and Q is also, just like A and Q is relative primes, the number K and Q is also relative primes. Then what Alice does is, Alice also computes G raised to K, and this value P is calculated, and Alice got G raised to A from, that is H is equal to G raised to A, which was part of the public key of Bob. Okay, so G raised to A is again exponentiated with the K value which Alice has selected. So now S is equal to G raised to AK, and Alice has also computed P, which is equal to G raised to K. Okay, now what she needs to do is that this G raised to AK is the number with which the message M is multiplied. And then what she does is she sends P, which is G raised to K, and the message into S, which is the cipher of the message, to Bob. So Bob gets G raised to K and M into S, where S is equal to G raised to AK. Okay, now both of them have generated their keys for the encryption and things like that. And now when Bob receives the message, what does Bob receive? Bob receives over here P, which is G raised to K, and M into S, which is equal to M into G raised to AK. Okay, so what Bob does is Bob calculates P raised to A. Remember over here, P is G raised to K. So when Bob does P raised to A, from P, the value P, neither G nor K can be separately found out. Okay, so he gets a value for P, that P he exponentiates with A, and it is in effect G raised to AK. So now P, the value which he has got when he calculates S dash, is S dash and S is the same. So Bob calculates P raised to A, which is equal to G raised to AK. Then what he does is he divides the message that he has got is M into S, and G raised to AK is equal to S dash, which he has calculated, and that is also equal to S. So if this S needs to be removed, all he has to do is he has calculated S dash. Now divide M into S divided by S dash, and he will get the original message because S and S dash are equal. Both are G raised to AK. Okay, so this is the method by which the message is calculated. So now just look at, once G is known and both A and B have selected A and K, then this is what is required. If we know G raised to A, G raised to K, and G raised to AK, which is calculated in the receiver and the sender side. This is G raised to AK is never sent over the web. Okay. Directly, A and K values are not sent. Okay, so S is the value. Here also S is not sent. See, here F and Q are sent with G raised to A. Okay, G raised to AK is not sent. And then over here, G raised to K and M into S is sent, M into G raised to AK is sent. So G raised to AK is not directly sent. Each in the receiver side and in the sender side, it is calculated. Okay, so G raised to A and G raised to K, once it is known, G raised to AK can be calculated on both sides, and whatever message is encrypted can be decrypted. Okay, and the reason this can be done is given over here on the right-hand side. In this crypto system, the original message M is masked by multiplying G raised to AK. To remove the mask, a clue is given in the form of G raised to K. But by knowing G raised to K or by knowing G raised to A, G raised to AK cannot be found. Unless someone knows A, he will not be able to retrieve the message. This is because finding the discrete log of a cyclic group is difficult, and simply by knowing G raised to A and G raised to K, it is not possible to compute G raised to AK. Okay, so now we are going to look at advantages and disadvantages. The advantages of Elgamal is that discrete logarithm problems are not easily solvable. They are hard problems, so they are secure. Okay. Then for key distribution, the same algorithm can also be used for key distribution because the encryption and decryption keys are different, making it easier to distribute the keys. Okay, both the encryption key and the decryption key are different. So even though we are sending information to calculate the encryption and decryption keys, they are not really the same. So even when we transfer the data, the transfer is secure. So the key distribution is secure. And the same algorithm can also be used for digital signatures, which allows for authentication of the messages. Okay, so these three are the advantages. And disadvantage is that Elgamal is a slow process. Okay, compared to other encryption algorithms, very long keys are going to be used. So it is impractical for some applications where fast processing is required. There, Elgamal will not be a good choice. Okay, another issue is the large key size. Okay, so the same level of security, if you look at other algorithms, here to achieve the same level of security, very large key sizes must be used. And this also might be difficult in some applications. Okay. In addition, it is vulnerable to an index calculation, an attack which is based on discrete logarithms. It is called index calculus algorithm. Okay, this can reduce the, not for all cases, but for some cases, it can reduce the security of the algorithm. And with this, we are concluding Elgamal, and you will see later on, Diffie-Hellman and Elgamal are very similar. Okay. Now, the next algorithm is Knapsack algorithm. Okay. So, in this particular algorithm, the security is in the difficulty in solving a certain combinatorial problem. The idea is that to encode a particular message, there is a base system. And from that base system, only the intended recipient will be able to retrieve the digits in the message. Okay. This particular system is not used at present, but it is there part of as a syllabus, and it's an interesting crypto system. So it is being taught. Okay, now knapsack problem, I hope all of you all know already. Knapsack in general, okay, knapsack means a sort of bag. Chak, nammade Malayalathil parna chak. Ee chakinte agathu, the volume of the knapsack is capital V, which is a natural number. Okay, so it is capital V, which is a natural number. And the purpose is to fill this knapsack, maximum V on a volume. Okay, we want to fill this knapsack with other elements which are also natural elements, objects with different volumes which are less than V. Okay, so A1, A2, etc., AR are all objects which have got volume less than V. Okay, now the problem, the knapsack problem is whether or not it is possible to choose a subset. So, kore sadhanangal undu, what we want is to select objects from this particular set in such a way that we can fill the knapsack. Okay, so if total volume is V, we want to fill those items which will actually give me V. So maximum, I want to fill the bag to the maximum. That is my problem. Okay, so now the question over here is, should I put A1 or should I not put A1? If I'm putting A1, then epsilon I or epsilon 1 will be equal to 1. Okay, if I choose not to put A1, then epsilon 1 will be 0. Okay, so what does it become? It becomes, does there exist epsilon I for R of these items, where epsilon I can be either 0 or 1, so that when, if it is 0, then that particular number, if epsilon of 1 is 0, then the A1 is not put into the bag. Okay, if epsilon of 1 is 1, then A1 is put into the bag. Okay, so now the question is, if we calculate epsilon 1 A1 plus epsilon 2 A2 plus etc. epsilon R AR, can we get V? Okay, solving this problem, which values of epsilon will be equal to the volume of the knapsack? This is the knapsack problem. Okay, and this is an extremely difficult question to answer. Okay, for example, now this is not the knapsack cryptography, this is the knapsack problem. Okay, suppose we have items A1 is equal to 2, A2 is equal to 5, A3 is equal to 6, A4 is equal to 9, and A5 is equal to 13. So there are 5 items, and V is given as 20. Okay, V is given as 20. So which of these items, if we put into the bag, we will get 20 is the question. Okay, so if you look over here, 5 plus 6 is 11, and 11 plus 9 is 20. So if we put A2, that is epsilon 1 will be 0, epsilon 2 will be 1, epsilon 3 will be 1, and epsilon 4 will be 1, and epsilon 5 will be 0. Then in that case, 5, 6, that is A2, A3, and A4. 5, 6, and 9 will be included. Look over here. Okay, so this has become equal to 20. Okay, so there is a solution for this particular V is equal to 20. But say that our V is equal to 23. Let's check whether there is a solution. There is no solution to the knapsack problem. And see what we are going to do. We notice that if we add 2 plus 5, these 3 numbers are 20. 20 plus 2 is 22. Okay, if we do 20 plus 2 is 22, then we need 1, which is not there in this particular set. Okay, so all epsilon 1, epsilon 2, epsilon 3, epsilon 4 are 1. If we put epsilon 5 is equal to 1, it is not a solution. And if we, try to remove, we must be able to choose one of these numbers in such a way that it is either 1 or 10. Okay. So there is, if whatever combination we take for these epsilons, epsilon 1 to 5, it is not going to give us the sum 23. So there is no solution for V is equal to 23. Okay. So this is just an example of a knapsack problem to show you that it's not an easy problem. Okay. Now we are going to look at something, different. That is super increasing sequences. What is this sequence A1, A2, A3, A4, A5 is called a sequence. Okay, now what is meant by a super increasing sequence? Because in the knapsack cryptography, we use super increasing sequences. Okay, so definition is, we say that a sequence A of I is super increasing if A of n, that is the last number, A of, in our example, A of 5, is greater than the sum of all the previous numbers. Okay, for all n, which is greater than or equal to 2. Greater than or equal to 2. So if you look over here, A1 is A2 must be greater than A1. If you look at A3, it should be greater than A1 plus A2. Here it is 7. Okay. So A4. So we can see over here, if when we look at 20, 10 plus 4 plus 3 is 17, which is less than 20. Okay. So this sequence A1 to A4 is a super increasing sequence. Now we'll look at the next one. 1 is less than 2. 2 plus 1 is 3, which is less than 4. 3 plus 4, 7 is less than 8. And 8 plus 7 is 15, which is less than 60. So this is also a super increasing sequence. Okay. Now, if we write this in general, the sequence will be A1 is equal to, say, 1, or given that B is greater than or equal to 2. Okay. So if B is greater than or equal to 2, then A1 can be equal to 1. A2 is equal to B. A3 will be B raised to 2. And AI will be equal to B raised to I minus 1. So AR will be equal to B raised to R minus 1. And this will be a super increasing sequence. Okay. So these super increasing sequences are used for the cryptography of knapsack cryptography. Okay. An important feature of solutions to knapsack problems involves super increasing sequences. Sequence is that they are these super increasing sequences are unique. And this is the theorem. The proof of this theorem we are not going to look at, but induction proof is used for the proof of the theorem. If you want, it is there in the 2 slides. You can go through it, but I'm just going to give you the statement. Okay. So if this set AI, which is a subset of N, is a super increasing sequence. If there is epsilon I and delta, comma delta I, which are both elements of 0 and 1, and sum of I is equal to 1 to R, epsilon I AI is equal to sum is equal to I is equal to 1 to R, delta I AI, then delta I and epsilon I will be equal for all of the i's. Only then these two things can be equal. Okay. When you sum all the values from I to R, if they are for 2 different super increasing sequences, if they are supposed to be the same, then epsilon I and delta I must be the same. They will be unique. And based on this, we are doing the knapsack cryptography. Okay. Now this is the proof, induction proof, you can go through it. Okay. Now this is the mathematical, reasoning in the cryptographic algorithm. Okay. It is relatively easy to solve a knapsack problem involving a super increasing sequence. It's not so easy to solve a knapsack problem if it is not a super increasing sequence. But if you have a super increasing sequence, then it is a relatively easy problem. How? These are the steps which we follow. Suppose we are given that V is the total volume of the knapsack, and it is an element of N, and we want to determine epsilon of I for all of the AI values in the super increasing sequence. So we want to determine whether epsilon of I will be equal to 0 or equal to 1. Okay, for all of the R values in the sequence A of I. Okay, so what do we do? Let N be the largest index. So we are first trying to find out what is the epsilon of N for A of N. Okay, so let N be the largest index so that A of N is less than or equal to V. Okay, so we already saw that in the sequence, if it is a super increasing sequence, and if it has to be, if anything has to go in the knapsack, then it has to be either equal to V or it has to be less than the volume V. Okay, so the largest item will be either equal to V or the less than V. Okay, then if in any case AI, that is A of any AI is greater than V, it will not be part of this. That epsilon can only be 0 because it cannot be put into the bag. The bag is too small for that particular item. So for all values of I which is greater than N, the assumption is that AI is greater than V. Okay. And for all values of I which is less than or equal to N, the assumption is that it will be below the volume of or equal to the volume of N. Now the question is, we have to decide whether epsilon of N is, we already know from our supersequence itself that A of N will be less than or equal to V. Since A of N is less than or equal to V, we can always include A of N. So epsilon of N will be equal to 1. Okay. And then what we need to do is, if we want V and we have already put A of N inside this, then we minus from the volume A of N, the volume of the object which is already put inside that, and we find the remainder and we check whether that remainder is there in this remaining A of I. Okay. And we keep adding till the value becomes V. Okay. So let's look at this. This is an example. The objects are A1 is equal to 3, A2 is equal to 4, A3 is equal to 10, A4 is equal to 20, and A5 is equal to 42. Our volume is given as 55. Now we want to know what are the values of A1 epsilon 1. So epsilon 1, 4 epsilon 2, this is these values, okay? A1 epsilon 1, A1, A2 epsilon 2, it's going like that. So we want to find the values of epsilon 1, epsilon 2, epsilon 3, epsilon 4, and epsilon 5. So we saw from the previous algorithm that if this value, A of N, which is over here, the highest value is 5. So if A of 5 is less than V, which it is in this case, so we have to put it into the bag. If we are putting it into the bag, epsilon 5 will be equal to 1. Okay. Then how much space is remaining? 55 minus 42, which is equal to 7. Only 7 spaces remain. Now, how do we decide which epsilons can be used? We look, where does 7 come? This is in increasing order. Remember, this is in increasing order. So 7 comes between 4 and 10. So it comes between A2 and A3. Okay, so from this itself, we know that A3 cannot be added into the bag, and A4 also cannot be added into the bag. So now we know that epsilon 3 and epsilon 4 are equal to 0. But 4 can be added. There was 7 space left. So 4 can be added into the bag. So epsilon 2 can be made equal to 1. Okay, now if you remove 7 was there, we put 4 into it. So now remaining is 7 minus 4, which is equal to 3. And 3 is directly equal to A1. So epsilon 1 is also equal to 1. Therefore, 55 is equal to 3 into 1 plus 4 into 1 plus 10 into 0 plus 20 into 0 plus 42 into 1. This is how we can solve the knapsack problem if it is a super increasing sequence. Okay. Now we are going to look at how the crypto system is done. Okay. The public key crypto system, which utilizes this knapsack problem, easy knapsack problem, was developed by Merkle and Hellman. So it is the MH algorithm in 1978. And these are the steps. Every user chooses a super increasing sequence with R elements. Okay. A modulus M is chosen, which is greater than 2AR. The last number is AR in the sequence, and 2 into AR, a value which is greater, M will be greater than 2AR must be chosen for M. And another value A is chosen, the multiplier A is chosen with A comma M is equal to 1. Okay. So now what we do is we have the value A we have the value M, and we have got the sequence AI given to us. Okay, so if we have to calculate for the next step, once we have got the sequence AI, M, and A, we are going to find out, calculate BI is equal to A into the sequence AI mod M. Okay, so what is BI? BI is A into AI mod M. Okay, and then the encryption key BI is published. Okay, so what is published is the value BI, which was calculated by getting AI mod M. Okay, and the secret keys are the sequence AI, I is equal to 1 to R, comma, M and A. M and A are not, none of these values are directly sent. Okay, but these values are used to calculate BI. Okay, so all these three values, M, A, and AI, which was chosen in the first step, are kept as secrets. This second step value is the published key, and it is sent over the net for as the public key. Okay, now this is for every user. Every user does this. Now to encrypt a message to the individual with the public key, what they do is that this is the public key of one particular person. The sender first, remember that these are the R number of bits. Okay, just like AI has got R number of bits, BI also has got R number of bits. The sender first converts the plain text into R blocks, because one bit can be used only with one bit. So if the plain text is a large number of binary digits, what happens is the block is divided into R bits. Okay, a given binary block, that is P, there are R bits, epsilon 1, epsilon 2, etc., epsilon R, is converted to the ciphertext by simply calculating epsilon I BI. So the corresponding bits in the published key is going to be multiplied with the plain text value, and that is the ciphertext. So this is also a collection of bits. Okay, because the transformed sequence BI is no longer the, when you do before doing the cipher, BI is super increasing, but afterwards it is not a super increasing set. Okay, sorry, when AI is selected, it is a super increasing set, but BI is not after the transformation is done. That is AI, when it is done, it no longer becomes a super increasing set. So because of that, determining the epsilon I from the value of C becomes a hard problem. Okay, so this is the security, because by simply because BI is no longer super increasing, epsilon i's cannot be calculated from C. Okay, now, excuse me, remember that C is equal to epsilon I BI and BI is equal to AAI. Okay, we're going to look at the decryption. Okay, so the decryption key is K of D is equal to A of I, that is that particular sequence A of I, comma, M comma B, where B satisfies A, B, that is A and B are inverses. So AB is equal to 1 mod M, which is easily computed with using the, we have seen earlier, extended Euclidean algorithm. If we have A and M, if we have the value A and we have the value M, it is going to be easy to calculate the value B. Okay, so the decryption is going to be done. Remember that the message is encrypted using K of E, and the person, when he's published this B of I, he knows what is AI, and he knows what is A and M and AI. Okay, so these values are enough to do the decryption. Okay, so here AI, M, and B are used for the decryption. The message the recipient gets is C. To calculate the message, what he does is he multiplies B into C mod M. Okay, so now let us see whether it is possible to get this B with the things that this, Bob has. Bob was the user, right? No, the user, whoever was the user, who, what, with this information, whether he's able to calculate. B, C is equal, what is C? C is equal to here. C is equal to epsilon I bi. Okay. So over here in C, when you put epsilon I bi, we get epsilon I bbi. Okay. Now what is bi? We saw over here, bi is equal to aai. Okay. So bi is going to be written as aai. But we know that ab is equal to 1 because they are inverses. So AB and BA are inverses. So that will be cancelled. It will become 1. And then there is only epsilon I, AI remaining. Okay. Epsilon I, AI is the, because AI is a super increasing, sequence. This value, epsilon I, AI, will be less than 2AR. Okay, which is less than M. Okay, so S, the original message can be retrieved. What was the original message? Let's go back. The here the original message is epsilon 1, epsilon 2, etc., epsilon R. Okay, and here, sorry, here we have all the epsilon I values, AI values we already know, so all the epsilon I values are known over here. And from that, we can calculate the original message. Now let's look at, it follows that S is equal to epsilon I, AI, where I is equal to 1 to R. Now the recipient can compute each epsilon 1, epsilon 2, etc., epsilon R using the procedure described, that is using this particular procedure. We will be looking at an example here. Supposing the block to be encrypted is that this plain text is 01001 and the super increasing sequence is given as 3, 4, 10, 20, 42. Okay, the same sequence that was given earlier for this example, 3, 4, 10, 20, 30, 42. Okay, and here the modulus M is given as 90 and A is given as 70. Okay, so we first multiply our sequence. This is the plain text. What we need to do is this particular sequence is not directly used. It is multiplied by 17 and modulo 90 is done. So when you do 3 into 17 modulo 90, you get 51. Please check in your calculator. 4 into 17 modulo 90 is 68. Similarly for 10, 20 and 40, it will be 80, 70 and 84. Now, this is the sequence that is used to create the ciphertext of this particular plain text. So the second element is 1 and the last element is 1. So we have 68 plus 84, which is equal to 152. So this is the ciphertext. Now, to decrypt, we compute 17 inverse, which is equal to 53 mod 90, then multiply 53 with the sequence. So 53, the cipher was 152. So 53.152 mod 90. When you do 53.152 mod 90, you get 46. And 46 in plain text will be that is the binary numbers, digits will be for this particular, the original sequence, it will be 4 plus 48. So it will be 01001. Okay, so the epsilon values are 01. 42 plus 4 is what is required to get 46. So we have 01001 based on this original AI sequence. The decrypting is done using the AI sequence and the encrypting is done using the BI sequence. Okay. So with this, we have completed the Knapsack crypto system, and we'll be continuing with the Diffie-Hellman in the next class.